Hello, in this video I'm going to relate some new mathematical discoveries I've made regarding impulse drive. Firstly, to review, the basic idea covered in other videos on my YouTube channel. If you have a sinusoidal force act on a system, it can displace itself without the need to interact with its environment. You can create such a system via two mirrored rotating unbalanced lever arms. To constrain the momentum of the radial mass to the path of a circle, you need a force. The corresponding reaction force would cause the entire system to move if there is nothing restraining it from doing so. The question I'm interested in is if you can not only design such a system that can displace itself, but accelerate itself as well. The answer to this question is what the following math in this video is concerned with. To model this system, we first split it into two subsystems, a radial system and a linear system. At every instant of time, the revolving radial mass has a certain kinetic energy as well as the linear mass. Somehow, these systems are coupled together. For now, we're not going to concern ourselves with how they're coupled together. We just generally define that the change in the kinetic energy of each mass is the difference between the energy going into and out of the corresponding system. Energy can leave each subsystem to enter the other subsystem, but it cannot exit the combined system. Furthermore, we define that the radial system has an inflow of energy denoted R, which we assume for now is constant. Thus, the rate of change of the kinetic energy in the radial system is the sum of this inflow R and the amount of energy leaving the linear system for the radial system, minus the amount of energy leaving the radial system for the linear system. Similarly, the rate of change of the kinetic energy of the linear system is the difference between the inflow and outflow energy from and to the radial system, respectively. But by applying a time derivative to the linear kinetic energy, we can also say that the rate of change of the linear kinetic energy is equal to the linear mass multiplied by the linear velocity and the linear acceleration. We can use this relation to redefine the rate of change of the radial kinetic energy in terms of these state variables m, vl, and al. We also have the exact same relation to similar state variables for the rate of change of the radial kinetic energy. Reorganizing this equation, we can see that the sum of these two mirrored systems of state variables is equal to the inflow of energy to the combined system. This creates a two-dimensional first-order nonlinear differential equation, which I know no way to analytically solve, except if we make a substitution such that we say that each term has the general form of one of the terms in the one-dimensional parametric representation of a circle's radius. This lets us change the problem to solving two different first-order nonlinear separable differential equations, which, due to being separable, have a known analytic solution. This is what you get when you plot these solutions out, with the caveat that the computed magnitude of the radial velocity Vr is purely complex valued or imaginary if you set the constant for the corresponding initial conditions k2 equal to 1, or less than 1. One of the solutions being complex valued is a result of the method we use to solve the differential equation. We mapped terms from the real space onto a circle, and physically it basically just means that these two equations are in phase with each other, which you can see in the graph. We can, however, force the resulting solutions to be real valued by changing r from a constant to a function of time. The resulting pair of differential equations is still separable and analytically solvable. This particular example, however, corresponds to a constantly increasing acceleration on the radial system. It doesn't just accelerate, it accelerates at a greater and greater rate over time. This is the plot of the solutions. So far in our analysis of this system, we have ignored an important physical aspect. We basically assumed that these two systems are independent of each other, but if they transfer energy between each other, then that cannot be the case. Normally, you could assume that a radial system is independent of a linear one, with the major caveat being that the linear one must be moving at a constant velocity. A useful analogy is to think of a spinning top in a train car. The dynamics of the spinning top don't change if the train car is moving at constant velocity. That's the same thing as if the train was not moving, which itself is a constant velocity, just a zero. But if the top is on a train that is constantly accelerating, things are different. Things are very different if the top is unbalanced and it trades energy with the linear system of the train to cause that acceleration in the first place. This idea is analogous but not equivalent to how the dynamics of a pendulum are different in an accelerating frame of reference, where at the bottom here we have the equation for the period of a pendulum with constant gravity, then changing gravity. The form of the equation doesn't change, but the period is now a function of time as gravity changes. The way that we fix this is we say the radial mass has some tangent velocity around the center linear mass, which we call Vr. The linear mass is the linear velocity VL, and the instantaneous velocity of the radial mass VR star is the sum of these other two velocities. By doing that, we can apply all the same logic to the kinetic energy of the systems, except defined using the squares of the magnitudes of the instantaneous velocities VR star and VL. And we arrive at the same solution, but specifically for the magnitudes of these instantaneous velocities. Once again, it's important to keep in mind that VR star isn't a velocity tangent to a circle, even though in the frame of reference where you're standing on the linear mass watching it move, it would be revolving around you in a circle. Because we have arbitrarily defined it to be constrained to this path, we still make no attempt to explain how it is constrained, we just assume that it is. Furthermore, we solved the differential equation that acted on the magnitude of VR star. VR star itself is a vector that is the sum of two other vectors. We do not necessarily know that the magnitude of VR star is equal to the magnitude of VR plus the magnitude of VL, but we do know via the triangle inequality that its magnitude is less than or equal to the sum of the magnitudes of VR and VL. Since we have explicit equations for VR star and VL, this allows us to define a lower bound on what VR should be to achieve the desired behavior of accelerating the system, where VR is the instantaneous magnitude of the tangent velocity of the radial mass along a circular path centered on the linear mass. If we further assume that we can control VR arbitrarily, like the radial mass if rotated by an electric motor that produces a pure torque with negligible linear components of force, and we can perfectly compensate against the extra reaction forces created by accelerating the linear frame to hold VR at any value we wish at any instant of time or orientation of VR's vector relative to this linear acceleration. Then we can define this lower bound, depicted in yellow in this graph, for what the value of the state variable VR should at least have in order to produce the desired effect of continuously accelerating the linear system, which as you can see is not a very useful lower bound to work with, at least when every system parameter, like the linear radial mass, is equal to 1. However, as we can see in this graph, changing the system parameters can make this lower bound more or less relevant and useful. That's all for now. Thank you for watching.